Now we like to make a brief discussion on internal combustion engine, particularly the thermodynamic aspects of internal combustion engine. Now, internal combustion engine, basically it is a heat engine where the thermal energy is converted into mechanical work. This is a heat engine where thermal energy is converted into mechanical work, and basically it will work continuously. So, it will work in a cycle, and we know that if, as an engineer, we want to have the maximum efficiency. So, if there is any working cycle we have to follow, first we will try to see that why can we not follow an ideal cycle like Carnot cycle. So, if we think of Carnot cycle for gas as the working fluid. Carnot cycle for gas as the working fluid. We have seen the limitation of Carnot cycle for vapor as the working fluid. Now, we try to examine the limitations of Carnot cycle as gas, with gas as the working fluid. So, we will have, this is the PV diagram of a Carnot cycle. One, 2, 3, 4. A cycle like this. So, isothermal, adiabatic, isothermal, adiabatic. Here we have got Q in, here we have got Q out, and out of the cycle we will have efficiency eta is equal to 1 minus Q2 by Q1. So, this will be 1 minus T2 by T1, and that is the maximum possible when these two temperatures T2 and T1 are specified. But the problem is that in gas, for gas as a working fluid, isothermal heat addition and isothermal heat rejection, they are almost impossible, okay, unless we have a very large engine with a very large surface area and with infinitesimally slow process. Okay, one may try to approach isothermal heating and isothermal cooling. Okay, one will not get exactly, but one may approach. Again, if you have to have this adiabatic processes, then we have to have fast processes. So, what we are having, that for part of the cycle we are having a very slow process, we need a very slow process, lower surface area, higher surface area for better heat transfer, and for part of the process we need to have very low surface area and high speed. Okay. So, it is difficult to design such a cycle, it is not practicable. Another thing, what happens, we see that the change in volume, total change in volume for the cycle is V3 minus V1. This is V3 and this is V1. So, that is the total change in volume. If we think of in terms of the engine, then this is nothing but the swept volume. This is called swept volume. So, this swept volume becomes very large. This swept volume becomes very large compared to the total work done. What does it mean? It means that the mean effective pressure MEP, that is very low for Carnot cycle. All right. So, swept volume large means very large engine, very large volume, but we are having a very small amount of work output. So, our MEP becomes very small. Now, this is only representative of the ideal process. In actual case, what will happen? In actual case, there will be friction. So, when we are having a low MEP without considering friction, when we will consider friction, we will see we will get very minimum output out of it, out of the cycle. So, cycle design is not possible, not practicable. Even somebody designs the cycle, friction etc. cannot be eliminated, and we will get very low output from the cycle. So, though thermodynamically the efficiency is very high, practically the efficiency will be low, and practically this cycle we cannot develop also. So, that is why with gas as the working fluid, one cannot have a Carnot cycle designed. So, one has to look for other type of thermodynamic cycles. Now, we know that internal combustion engines, they are very versatile equipment, they are very useful equipment, and in those equipment the combustion takes place inside the engine itself, and the hot product of combustion that pushes the piston, and we can get work output out of it. So, internal combustion engine, let us have some small idea regarding the working of internal combustion engine. If we see the PV process of internal combustion engine, actual internal combustion engine will be something like this. This is PA or atmospheric pressure. So, there are basically two loops. One is called power loop and another is called pumping loop. So, one can explain the process in terms of so basically what I have shown is the piston cylinder arrangement. This is the cylinder, this is the piston, and these two are the two extreme position of the piston. Okay. So, sometimes, or this is called one dead center of the piston, this is the outer dead center of the piston, and this is the inner dead center of the piston. So, piston has a reciprocating motion between these two dead center, inner dead center and outer dead center. All right. Now, basically there are four processes. Okay. If we consider, of course, there are two types of machines, but if we consider the general working process, then there are 4 processes. So, the 4 processes will be intake, then compression, then expansion, and then exhaust. So, these are the 4 processes which we will have. So, basically if we see the 4 processes in this 2 loop or in this diagram, PV diagram, one can have 1, 2. So, we call it 1, 2, then 2, 2, 3. So, 2, 3, then 3 to 4, 3, 4, and exhaust 4 to 1. Exhaust is 4 to 1. So, in the intake process, what happens? And there are, in this piston cylinder arrangement, there are 2 valves. One of them is inlet valve and another is exhaust valve. Okay. So, in the intake process, what happens? The piston that moves from the outer dead center towards the inner dead center, reducing the pressure inside. The pressure inside that falls below the atmospheric pressure. I have shown the atmospheric pressure somewhere here. So, during process 1 to 2, the pressure falls below the atmospheric pressure. So, air is sucked in, either air or air fuel mixture is sucked in inside the engine cylinder. Then both the inlet valve and exhaust valves are closed. The piston have a outward movement from inner dead center to the outer dead center. At that time, either the sucked air or the sucked air fuel mixture is compressed. That is the compression process. Towards the end of the compression process, if we have sucked air fuel vapor mixture, then an ignition is created with the help of a spark plug, which is symbolically shown here, or towards the end of the compression of air, we inject fuel, liquid fuel, in the form of fine spray. So, so that fuel air mixture then get further compressed and evaporated and ignition takes place. So, in both the cases, in case of air fuel mixture or in case of air, compressed air with fuel injected in it, we have an ignition and combustion of the fuel. Then in the combustion process, due to the combustion process, pressure and temperature increases and that pushes the piston in the towards the inner dead center. So far we have seen in the suction process, in the compression process, that some external agency is needed to move the piston. Now what we can see that now due to the combustion, the gas inside the engine is having enough motive power to push the piston from the outer dead center to the inner dead center. So, now we get some useful work. So, the hot and high pressure gas, it pushes the piston and by that process it also goes to a low pressure and its temperature falls and it does the amount of work it was supposed to do. Piston is at one end, the entire engine cylinder is now filled up with spent gas which has done the work. So, this gas has to be expelled out of the engine, so that again fresh charge can be taken, again this cycle can start. So, then the piston has to move from inner dead center to the outer dead center while the exhaust valve is open. So, the gas pressure will rise above atmospheric pressure and the spent gas will go out of the engine. So, this is what we have in a nutshell in an internal combustion engine. Now, the process is complex, all right. So, we generally when we do the thermodynamic analysis, we do certain amount of idealization. The, the idealized cycle, we call it air standard cycle. The idealized cycle is called air standard cycle. Air standard cycle, I can represent any air standard cycle here. It is assumed that both the suction and the exhaust, these two processes, or intake and exhaust, either we call it suction or intake and exhaust, these two processes takes place at atmospheric pressure. So, instead of this loop, we will have a straight line. Okay. Instead of this loop, we will have this straight line. So, it is pointless to carry this thing along with the cycle diagram. So, we can do away with this straight line also. So, let us say this is one representation of an ideal cycle, all right. And then, so abolition of the suction and exhaust process, that is one of the attribute of the air standard cycle. Then we assume that air and only air is the working substance inside. That means, air is the working substance and it does not change its chemical property during the process. Okay. It does not change its chemical property, chemical composition during the process. So, the combustion process which takes place inside the engine, that is replaced by some sort of reversible heat addition process. Okay, by a reversible process in which heat is added from some external agency, all right. And again we have got some sort of a reversible heat rejection process. Moreover, one assumes that the specific heats that remains constant during the process, there is no change of specific heat. Actually, though there will be large amount of change of pressure and temperature, we assume that the specific heat does not change. So, this is what is air standard cycle, because we want to first idealize the cycle and then we can see what is the performance of idealized cycle and vis-a-vis the actual cycle. So, one can have the air standard cycle instead of the actual cycle for the thermodynamic analysis. Now, we know that basically internal combustion engines are of two types, SI engine and CI engine. For SI engine or for petrol engine, the idealized cycle is known as the air standard Otto cycle. Air standard Otto cycle. In the air standard Otto cycle, we will have adiabatic compression of air from 1 to 2, then this is actually V and this is P, constant volume heat addition from 2 to 3, then adiabatic compression from 3 to 4, and then constant volume heat rejection from 4 to 1. All right. These two are adiabatic processes. PV to the power gamma is equal to constant. All right. So, this we will have, and there is one important parameter, compression ratio. So, we will have V1 by V2, that is the compression ratio. What one can relate this thing to the engine parameters. V1 is the volume inside the cylinder and V2 is the clearance volume. Okay. So, by this one will get compression ratio, and I like to represent it with R. R is the compression ratio. Then efficiency Otto is equal to what one can write is 1 minus Q2 by Q1, 1 minus Q2 by Q1. So, one can write 1 minus CV T4 minus T1 divided by CV T3 minus T2. Okay. So, this is what we can write. So, basically eta Otto is equal to 1 minus T4 by T1 divided by T3 T2. So, one can write 1 minus, well, T1 by T2. Here one can write T4 by T1 minus 1 and T3 by T2 minus 1. This is what we can write. Now, one has to find out the relationship between different temperatures. Actually, if we look into the cycle, so there are 4 nodes 1, 2, 3, 4, and relationship between the 4 nodal points, 4 nodes, strategic points, 4 strategic points, that is important, and that one can find out very easily. Actually, what one has to use, one can use ideal gas law, because we are analyzing the air standard cycle where air is assumed to be an ideal gas. So, one can use PV is equal to RT. So, that relationship is there, PV is equal to RT, and then for 2 paths, that means PV to the power gamma is equal to constant for 1, 2 and 3, 4. These two paths PV to the power gamma is equal to constant. So, these two condition we can use and we can determine the relationship between different temperatures. All right. So, now now what one can write that T2 by T1 basically one can start from this point. Basically one can start from point 1. Why? Because here this is the intake point and generally this point is taken equal to the atmospheric condition. All right. So, one can start from here and one can move along the cycle. So, T2 by T1 is equal to V1 by V2 to the power gamma minus 1. So, is equal to V4 by V3 to the power gamma minus 1. So, is equal to T3 by T4 is equal to R to the power gamma minus 1. V1 by V2 I have defined as compression ratio or R. So, what we get is like this: T2 by T1 is equal to T3 by T4 or T4 by T1 is equal to T3 by T2. So, now I will write down forget about it. I will start from this point. Let us say eta Otto is equal to 1 minus T1 by T2 into T4 by T1 minus 1 divided by T3 by T2 minus 1. So, these two quantities are same. So, it can be cancelled and then one can write it is 1 minus 1 by R to the power gamma minus 1. So, this is what we can get from our thermodynamic analysis of the cycle, and R is the compression ratio. R is the compression ratio. All right. So, for ideal analysis of ideal cycle, one can take gamma to be 1.4. Okay. In other cases, one can take different values of gamma, but for ideal cycle, one can take gamma is equal to 1.4. All right. What one can see that the efficiency of Otto cycle, it can be increased by increasing R. Gamma we do not have much control, it is a property of the gas or the working fluid, and for working fluid we do not have infinite amount of independence. selecting an working fluid. But R probably we can do something, we can select higher values of compression ratio. Okay. Now, the problem with selecting higher values of compression ratio with the conventional design and conventional fuel of the internal combustion engine is that before you produce the spark, auto ignition will take place. Okay. So, it will ignite automatically or of its own before you produce the spark, and that will give uncontrolled combustion, which is not desirable. So, that is why we have got a limitation on the value of R, and that is why for petrol engine or for SI engine the compression ratio is generally small compared to its counterpart, that is diesel engine. So, we will have a lower value of compression ratio. Now, we go for the other type of arrangement. So, in this case basically the Otto cycle is suitable for SI engine, spark ignition engine, where what we do that when the air is being sucked in the airstream itself, the fuel is sprayed. That means, before the air comes into the engine, the fuel, and with the help of a carburetor we do it, and the fuel comes evaporates in the airstream. So, a fuel vapor mixture is formed, that mixture then enters the engine. So, that is one way of having the internal combustion engine. Another thing what I have told, that if we have air only, then we can compress it to a very high value. There is no no fear, there is no chance of having any combustion, because there is no combustible vapor in the air. So, we can compress the air to a very high value, and then only we can inject fuel in it. So, that type of engine is known as diesel engine, and the cycle, that is also known as diesel cycle. Diesel cycle, and that type of engine is basically known as CI engine, that is compression ignition engine. The PV diagram of the diesel cycle will be something like this. This is the PV diagram of the diesel cycle. We can have side by side the TS diagram also. So, 1 to 2 is the adiabatic process, 2 to 3 there will be rise in temperature, 3 is the highest point, and like this 1, 2, 3, 4. Something like this. So, this is Q1, this is Q2, and well, these two are PV to the power gamma is equal to constant. All right. So, efficiency diesel the efficiency of diesel cycle, that will be Q1 minus Q2 divided by Q1, work done divided by the energy supplied. So, this will be how much? This will be 1 minus Q2 by Q1. So, this is 1 minus Q2, that is a constant volume heat rejection process, CV T4 minus T1 divided by Cp constant pressure heat addition T3 minus T2. All right. So, at this point we want to define a few quantities. Let us define R is equal to compression ratio is equal to V1 by V2, that is the compression ratio. Okay. So, where V1 is the total volume of the engine and V2 is the clearance volume. All right. So, already we have seen it in Otto cycle, it is the same quantity, and then we have got cutoff ratio RC, that is cutoff ratio, we call it V3 by V2. So, physically it means that at point V3 the fuel supply is cut off. We start supplying the fuel at point 2 and at point 3 the fuel supply is cut off. So, this is your cutoff ratio. Now, I will not go into detail derivation. So, basically what one has to do here, again one has to get the relationship between different temperatures. I mean, I can do slightly ahead and then I can leave it to you. Eta diesel, that is 1 minus Cp by Cv, one can write 1 minus, one can write Cp by Cv, that is what, and then one can have T1 here, then T4 by T1 minus 1, and one can have T2 here, then T3 by T2 minus 1. All right. So, basically we have 1 minus 1 by gamma into T1 by T2 into T4 by T1 minus 1 and T3 by T2 minus 1. Well, now just the method we have followed earlier, one can do the analysis, and if we do the analysis, we will have a much cleaner expression. Eta diesel, we will have 1 minus 1 by gamma r to the power, that is 1 by r to the power gamma minus 1, then the top r c to the power gamma minus 1, this you will get, and here you will have r c minus 1. So, this will be the formula. So, basically again eta diesel, that will be a function of gamma, then r and r c. All right. Well, here of course, we do not have much restriction on r, we can increase r. In fact, in CI engine we have got CI engines, we have got high compression ratio. Only problem is, more the compression ratio, more bulky will be the engine. Engine weight will become larger and larger to withstand the pressure fluctuation. One side we are having low pressure, almost near to atmospheric, and other side we have got a much higher pressure. So, engine will be bulkier. So, again there are practical limits. So, we cannot go beyond certain value of R. RC also, one should restrict it. Let us say this is the engine cycle diagram. If we have got lower RC, then enough amount of fuel cannot be injected. If you have got higher RC, then what we can see that we are not getting large amount of work due to the expansion. So, one has to compromise between these two. All right. So, the diesel engine we will have, or diesel cycle rather, diesel cycle we will have the efficiency in terms of these quantities. Then in fact, we have idealized the combustion process by two different techniques or by two different ideal processes, reversible processes. First, we have thought that the combustion process can be represented by a constant volume heat addition process. Okay. And next, we have idealized that the combustion process can be idealized as a constant pressure heat addition process. In fact, the combustion process is so complex that it cannot be idealized either by constant volume process or by constant pressure process. But what has been seen at the initial stage of the combustion, there is very quick increase in pressure, the volume remains almost constant, and after that pressure remains more or less constant, but there is increase in volume. So, people thought that probably a better representation of the process will be if we have both pressure, constant volume and constant pressure process. This cycle is known as a mixed pressure cycle or dual cycle. So, dual combustion cycle or mixed combustion cycle or mixed pressure cycle, something, there are different names for the cycle which I am going to describe. So, ideally the cycle is something like this. pressure, volume, then so basically we start from 1.1. So 1 to 2 is the compression process, then 2 to 3 is the constant volume heat addition, then 3 to 4 is the constant pressure heat addition, 4 to 5 is the adiabatic expansion, 5 to 1 is the heat rejection process which takes place at constant volume. So, what we can have both through these two, we have heat addition. So, we have Q1, then you have Q2, these two are adiabatic processes, this is constant volume, and we can have a TS representation also, ST. This is constant entropy process, that means reversible adiabatic process. This is 1 to 2, then this is a constant volume process 2 to 3, constant pressure process 3 to 4, (4 to 5) adiabatic process, and 5 to 1 constant volume heat rejection process. So, this is how we will get the cycle. Now, the efficiency of dual combustion cycle or mixed combustion cycle will be Q1 minus Q2 divided by Q2, that is equal to divided by Q1, this is the heat addition. So, it will be 1 minus Q2 by Q1. So, let us start from eta dual is equal to 1 minus CV constant volume heat rejection process T5 minus T1. There are two heat addition processes. So, this will be first CV T3 minus T2 and plus CP T4 minus T3. At this point, let us define R, that is compression ratio, that will be V1 by V2. Then we have got pressure ratio, that is P3 by P2, and we have got cutoff ratio, that will be equal to V4 by V3, that is equal to V4 by V2. So, pressure ratio we call it RP and we call it RC, cutoff ratio. And if you introduce all these things, then you will get eta dual is equal to 1 minus RP RC to the power gamma minus 1, then R p minus 1 plus gamma R p plus gamma R p R c minus 1, and this whole will be R to the power gamma minus 1. Okay. But thing is that this is the general expression, this can be taken as the general expression, and if we put, let us say, R p is equal to 0, we will get the expression for diesel engine. Okay. So, that we can check also. R p is equal to 1, not 0, sorry, R p is equal to 1, then we will get the expression of
R c equal to 0, then we will get expression for Otto.
Yeah. So, we can try those things. You can, first thing you can try the derivation of this big equation, and then you can try all these things. All right. So, I think we will stop here and we will continue from this point in our next class.